All right, this is part 4 of the 4 things to know about the gradient. Remember, we've already covered 2 things to know about the gradient. One is the definition that the gradient is f sub x times I plus f sub y times j. In other words, it's a vector whose components are partial derivatives of the function. That's thing number 1. Thing number 2 is that we can use the gradient to find directional derivatives in a given direction by taking the dot product of the gradient vector with a unit direction vector. That's thing number 2, is we can find directional derivatives easily from the gradient by using the dot product. Okay, now, thing number 3. To see thing number 3, we're going to try thinking about this dot product here in a different way. Remember, anytime you see a dot product, there are really 2 ways to think about the dot product. One is algebraic, and the algebraic way of thinking is what got us to this formula here. We got it by thinking of an expression as some number times some number plus some other number times some other number. That's a dot product naturally. But the other way of thinking of a dot product is geometrically. That is, I can think of f sub u at p as the dot product of these 2 vectors, which is the product of the magnitudes of the 2 vectors times the cosine of the angle between those vectors. Now this time, I'm not making any assumptions about the vector u. I'm not going to assume u is in a particular direction. I'm going to let that direction vary. So I'm going to let it vary around the point P. It could go this way, or it could go this way, or it could go some other way. I think my arm was invisible there because I was standing in front of it, so let's try again. So you could go this way, or this way, or this way, or any other way around the point P. Now let's take a look at this expression once again. Notice there's something here that you already know the value of. You know that the magnitude of this unit vector is 1, which means that my directional derivative in the direction u is the gradient of f at p times the cosine of the angle theta. Now let's play a game. Suppose I want to make the value of this expression as big as possible. I'm not allowed to change the gradient because I'm at the point P already. That was the point 1, negative 2. And I'm not allowed to change the function. It's already given. So I can't change the gradient at all. It is what it is. The only thing that I get to change is the direction u. So you can go in any direction you want from the point P, and you want to make the rate of change in that direction as large as possible. How would you do it? What in this expression would you actually be able to change? We can't change this because P is given, F is given, the gradient's given. The only thing that we can change is the angle theta between the gradient vector and the unit vector. That's the only thing we have the power to change. Now, how would you set the unit direction vector so that this cosine theta is as large as possible? Well, you remember that the cosine theta can only be as high as 1. That's the highest it can go. And it will take that value. This will be as large as possible when u is in the same direction as the gradient. Because I need to make the angle between those 2 vectors 0 in order to get the cosine to be 1. Which means if I want to travel from P so that I have the greatest rate of change possible, I really want to go in the same direction as the gradient vector. That is the same direction as the vector 2i minus 4j. Now that's not what u is going to be, because u has to be a unit vector. Which means in order to find u so that this is maximized, to maximize f sub u at p, I need my unit vector to be in the same direction, just unitized. To unitize this, I need to divide by its magnitude, which I calculated earlier. The magnitude is, well, let's just write it out. Magnitude is going to be square root of 4 plus 16, which is root 20. So my unit vector is going to be 2 over root 20 I minus 4 over root 20 j. And I'm very deliberately leaving this unsimplified so that we can see where all those numbers came from. You could simplify it by eliminating a factor of 2 in each of these, but I really don't see the point. I like it better this way. Okay, so that's the unit vector that will give me the greatest directional rate of change from the point P. And you'll notice it goes in the same direction as this, so I can actually guess in my picture about where that's going to go. It's going to go a little bit in the x direction and more in the negative y direction. So it's going to look something like this. But let's review what we've done here. Because what we've shown is that the maximum rate of change from P can be found in the direction of the gradient. That's something you've heard before. It may have been stated a bit differently. I think what you heard from the book or from your instructor is that the gradient gives the direction of the maximum rate of change at P, or the gradient is the direction of the maximum rate of change. What is that maximum rate of change, by the way? What is the maximum value of this expression? We said the maximum value of the cosine could be 1, or is 1, which means the maximum value of this expression really is just this magnitude here. So the maximum rate of change, or the maximum directional derivative, is the magnitude of the gradient, which in this case was square root of 20. So that's the third thing to know. I guess really it's two things. One is that the gradient gives you the direction of the maximum rate of change. Okay? The gradient gives you the direction of the maximum rate of change of the function at a point, and that maximum rate of change actually is the magnitude of the gradient, which is pretty cool. A lot of students, by the way, often say that the gradient is the maximum rate of change, and that's not true. The gradient can't be a rate of change because the gradient's not a number, it's a vector. So make sure you have those two things disentangled. The gradient is the direction, or it's in the direction of the maximum rate of change, and that maximum rate of change actually is the magnitude of the gradient, which is just a nifty coincidence. Actually, I don't believe in coincidences in math, but it's pretty cool. That's thing number 3. Now, thing number 4. Let's look back at our contour diagram. It looks like, from the drawing, the gradient appears to be perpendicular to this contour curve at this point. Is that a coincidence, or is there a reason for that? Well, let's suppose I draw another contour. Again, this one's going to be closer because the function increases much more rapidly as I go out from the origin. Yeah, I'm sorry about the sloppiness of this drawing. It's like a Simpsons drawing of a contour diagram, but I think it's visible enough. If I look at a contour diagram and look at some point in the contour diagram, and I think, what would it take to get the maximum rate of change of the function? Well, if I want the maximum rate of change of the function, that means that I want to head towards the next contour up as quickly as possible, which means I need to go from this point to this next curve in the most direct way possible. Normally, if your function is differentiable, the best way to get to the next contour quickly is going to be to head out perpendicularly from the contour that you're at. That's why the gradient vector is always, assuming a differentiable function, it's always perpendicular to a contour at a point, because that's the direction that gets you to the next contour the fastest. And I'm not sure whether that's said in the book, but it deserves to be said here. There's a reason why the gradient vector is perpendicular to a contour, or in general to a level set, and that's the direction that gets you to the next level set the fastest. That's an important distinction because gradient vectors are not, in general, perpendicular to the graph of a function. A graph of a function is a very different object from a contour or a level set. Gradient vectors are perpendicular to level sets. Remember I said in the first video, it wouldn't make sense for the gradient vector to be perpendicular to the graph, because the gradient is just something that lives in 2 dimensions, and this graph lives in 3-dimensional space. But it makes perfect sense for the gradient to be perpendicular to the contour, because that is an object living in the 2-dimensional plane. So that's the fourth thing, is that the gradient is perpendicular to a level set of a function, All right, so those are the four things. Number one, definition of gradient. It is a vector whose components are partial derivatives. Number two, directional derivative is the dot product of the gradient with a unit direction vector. Number three, the gradient gives the direction of the maximum rate of change, and that max rate of change is the magnitude of the gradient. And number four, gradients are perpendicular to level sets, not graphs of functions, level sets. All right, so I know that that was a long lecture if you look at all 4 videos put together, but I hope that that was useful. I hope you will leave a comment letting me know what you understood better and what helped, and if you have any questions. Thank you.